Hello, everyone. How are you? Good, great. So today we are going to speak about LLMs. So you know it's the explosion of LLMs everywhere. Certainly you are using them for your, in your company, or you plan to use them. Or maybe as an individual, you are using them with ChatGPT. Today we are going to speak about LLM, but we are at RSA, so we are not going to speak about the machine learning side of it. We are going to speak about security and in particular privacy. We are Zama. We are a French open source startup working on top of fully homomorphic encryption, so FHE. And in particular, we build tools for developers for them to add privacy in their application without needing to know anything about the crypto. So we try to make tools which are open source and which are easy to use, so that they can use the benefits of FHE without really needing to understand how it works. So today I speak with Jordan. Jordan, if you want to introduce yourself.
Yes. Hi, I'm Jordan. I work at Zama for about 2 years now as a research scientist, and we develop tools to bridge the gap between machine learning models and FHE, where the main idea is that we want to run machine learning models, AI models, on encrypted data. Before that, I did a PhD in machine learning, and I worked as a data scientist in different companies.
Okay, great. And on my side, so I'm Benoit. I'm the VP of machine learning here at Zama. So mainly I oversee two teams and products. So the first one is ConcreteML, which is our machine learning framework over encrypted data. So here, more or less, you can do machine learning or deep learning, but over encrypted data. And the second product and team is Concrete, which is actually our FHE compiler. So here, more or less, you can compile, which means you can turn your Python program into its FHE equivalent. So let's diving into the subject of today, so LLMs. So LLM story, let's say that it started in 2017 when some Google researchers invented the principle of transformers, and then it was the start of a big explosion. We've seen some new models every year, and more of them. At the beginning, things were in the open, which are the green models, with ChatGPT and with other companies joining. And then we have seen a few new models, and especially the closed models, which appear, and now we have a few companies that you know, so OpenAI, Google, Apple, which is pretty new, Mistral, and so on. And you know these figures that we have updated 3 weeks ago is already outdated. Already we have new models which are already better than these ones. And then when we think about LLMs, there is something that we have to have a look to, which is privacy. So for example, you are using LLMs in your company to help you code. So you are asking the LLMs to help you to code a new function. And when you do that, you are sending some data about your company secrets, about what you are planning to do to some third party, and it may leak things which you would want to keep private. So it's really bad. You should keep those things for you. Same thing when we are speaking about individuals. You don't want to share your health data or your financial data with anyone. That's something that you would like to keep for you. When you use ChatGPT, when you use LLMs, today you share those things. which is bad because you share those things with the AI company. And what could be even worse is that if ever those data are kept to fine-tune the model later, it may make that in future queries made by your, for example, competitors, your private data may be part of their answer. So, for example, you are, I don't know, Samsung. You've put some information about your company, and then later Google guys are going to ask the ChatGPT and are going to see some of your private data. So it's really something that you would like to avoid. So what are the solutions to this kind of problems? The first kind of solution is you try to do everything by yourself. So you build your own LLMs. It's going to be complicated. Building an LLM is expensive and requires some knowledge. So it's really restricted to a few companies. Certainly, you shouldn't do that. The second kind of solution is to try to use some open source models. Maybe you are going to fine-tune them a bit. It's not going to work because those open source models are not as accurate, as good as the closed source models. So for example, on the right, we have put a ranking of some models. And you can see that the best models today are the closed models. Same thing, this ranking is outdated. It was done like 3 weeks ago. And finally, maybe the best solution today is to deploy the LLMs on-prem, which means on your servers. But then there is another problem. It's no more the privacy of the queries, which is a problem. It's the intellectual property of the models. I mean, closed source company wanted to keep their model private, and then they deploy these models on servers which are not their own. So those models may be, looked at by competitors, and the weights may leak, which is something that those AI companies don't want. So what we have tried to do in the team, in the company, is to use AFHE, fully homomorphic encryption, to solve this problem. So at the same time, having the user's privacy, but also preserving the intellectual property of the models. And so we are going to show you what we have been able to do with AFHE. I'm going to remind you a bit what AFHE is. So it's another hot topic today with LLMs. So what is AFHE? First, let's have a look to the current situation with HTTPS solutions. So in HTTPS solutions, when you have like a client and a server, what you are going to do is that you are going to encrypt the data, so X, on the client side. You are going to send it to the server. And then on the server side, things are going to be decrypted, which means that the data are secured during the transport, but once it's on the server side, everything is in the clear. So the server will be able to compute the function f, but the server sees your data, and if ever there are like security breaches on the server, your data might leak. So this is HTTPS, and with HTTPZ, so the fully homomorphic encryption version, what we want to go further in the security. So here we are encrypting the data with a key on the client side, which is only known by the client. We send this to the server, and the server will never have the private key, so will never be able to decrypt things in the clear. But still, thanks to some mathematical properties of fully homomorphic encryption, it's possible to compute the function f with only public key information at the end, you will have an encryption of f of x, and you will send it back to the client, which will be the only one able to decrypt this in the clear and get the final result. So this is FHE. This is what we are using. Last year, we were already at RSA, the same pair of speakers, to explain how we use FHE for machine learning model. And here we are going to show you how we use it for the LLM use case. And then just to give a bit more of information on which FHE scheme we use. So we are using a scheme which is called TFHE for Torus fully homomorphic encryption. So that's not important. The important part is that in this scheme, you can do additions of encrypted values. You can do multiplication of an encrypted value with an integer, and you can apply table lookups over the integers, the ciphertext, sorry. And in particular, it's possible, but it's slow to multiply ciphertext together, so encrypted values together. We are going to see when we speak about the LLM that it will be one of the bottlenecks in terms of speed. It's doable thanks to the table lookup primitive, but it's slow, and it's what makes our implementation today sometimes slow. And now let's speak about LLM.
All right, so before diving into a bit more technical stuff on how we can achieve LLM on encrypted data, so we are developing a tool where all basic models that are used in the industry can be run on encrypted data, like linear models, tree-based models, and even neural network. And today we are exploring how we can make those gigantic models that are being released run on encrypted data fast enough. So all of this is going to be open source and available on GitHub. So if you want to try it out, you can. We also wrote a blog, which I will come back a bit later. All right, so it's going to be a bit technical here, but the main point is to look at what kind of operation, basic operation, are in large language models. So this kind of graph figure on the right that you can see is often used to show how LLM work. But in the end, it boils down to very few operations. The first thing that you can see is at the beginning, so the beginning is at the bottom, is the embedding part, right? The embedding part, so first, maybe I should start. What you do, the first thing that you do is convert text into something that the machine learning model can use. And text is not good for that. So what you do is tokenization. So you transform every, let's say, word into an ID. That's it. And embedding transform word into the ID into a vector, right? And this operation is simply a table lookup, right? See, in most of the LLMs that we see today, the size of those table lookups can vary, but it's tens of thousands of different words. Actually, it's not words, it's tokens, but let's say words for simplicity. And what you have to apply is a simple table lookup. This is possible with the FHE scheme that we are using. So this is all fine. We can execute this part in milliseconds. Now, the second part we're going to see is the feed forward. The feed forward is on the right figure, is at the top. So this is the linear GLU linear. GLU is just a nonlinear activation function, right? And these two linear things are simple linear transformations. So you have a matrix of weights, and you apply this onto the inputs, and you get a representations given by the weights of your model. Right? You apply nonlinear activation, and then you're back to the linear parts, right? So mathematically, it's simply applying a function over the linear transformation. And then you do that again with another set of weights, right? So this is doable in seconds or even less, depending on the machine you use behind the scene, right? So today, to give you an idea, these linear parts, something I mentioned, the most right part is basically a transfer block. And today, the way you make a model better, I'd say, is scaling up, is basically stacking over and over these kind of layers. So, but each layer is the same from the architecture point of view, right? So these parts, these linear parts, are somewhere around thousands of values, which in FHE will be like thousands of ciphertext, right? And so we're going to have to apply a nonlinear activation on every single value that we have here. But it's very doable. Now comes the funny part, which basically was discovered in 2017, where people were working on natural language processing and wanted to have a way for the model to see all the text at once. And this is called the attention. The attention mechanism allows the model to essentially put some weight on all the words that it sees. Right, so how does it work? It's basically 3 linear transformation. You have Q, K, and V here, which you take the input, which is X, and you transform X 3 times into different representation, right? You end up with Q, K, and V. In the FHE world, these 3 Q, K, and V are going to be encrypted. So what comes next is the bottleneck. The attention multiply the Q with the K. So here you have encrypted multiplication that scale quadratically with the number of words. So the longest your document is going to be, the hardest is going to be, the most impactful is going to be on the performance here. And it's basically like for current LLMs. They try to increase the context as how many words you can actually put in the context of your LLM. But the problem comes from these Q and K, which grows very, very much. And for us, it's even more because we have to do a costly operation. You might have heard from Benoit, it's the programmable bootstrapping, which costs less than a second, but you have to do that a lot of times, right? So the softmax is another operation that can be a bit costly, but you don't have to apply this a lot of times. But then comes another encrypted matrix multiplications with V, which is the third representation, right? So this is quite costly. It can be minutes or hour, right? And here we are talking about the next token prediction. We are not talking about when the LLM finishes predicting, generating the new text. So it's a bit too long, right? So we have written a blog on this, showcasing how fast we should go and how parallelized our hardware should be to actually execute the large language model with FHE end-to-end. And until GPU, so we are currently working with GPUs to speed up the process, but until we get there, we need a way to make the operation faster, right? And actually just trying to get rid of this attention part in FHE. And this is where comes the hybrid model. So here the main idea is that we are going to want to protect the IP, and we're going to look where is the IP in LLMs, and we want to secure, to protect the privacy of the user, which is where comes the whole game today with LLMs. And we will be able to do this by splitting stuff between the client, which wants to have a prediction from a large language model, and the server, which can execute stuff in FHE, but it might not be needed to execute the whole thing. So the first question is, where is the intellectual property located? Well, in a neural network, you have two things. The first thing is the architecture. This is what I'm showing here on the right part. This is something that is known. I can't know for sure, but there is no secret in large language models that are currently under API and not being released. There is no secret in the architecture. We all know because it comes from the research, the public research. So there might be some tricks, few tricks, but it won't change the overall accuracy. You might gain a bit of performance, but that's it. So where is the actual IP? It's in the weights. When you train a large language model from scratch, and this is one of the solutions that could help you have LLM private for yourself, you're going to have to pay a lot. And a lot is in the order of millions of dollars to just train a model. And I'm not even talking about the engineers you're going to have to recruit to actually make this model train, because it's not easy to have the data, to clean the whole stuff, and have a final model that does exactly what you want. So once they trained their model, they thought they had a good opportunity to sell a service because weights they learned are actually the whole IP. This is how they can actually make business. So keeping the weights on their server and just offering the exchange with users under the API, right? So here I'm taking an example, which is a recent, again, a lot of different models came out, but this was a month ago, the GMA with 7 billion parameters from Google. And what we can do here is look at where are the weights located. So some of the weights are located in the embedding. We know that it's very easy to do this with FHE, but most of the weights are located in the feed forward, which are the two linear at the top on the most right in the figure. And all the weights of every model are located in the linear part. So what this means is that we can focus on a subpart of this. We could also do the embedding here as well. And we could get most of the IP of the large language model, right? We don't have to actually do the whole thing. We can split and do only a part so that the IP is preserved. So this is how it looks like in practice. So the clients want to query an LLM and has a secret key. It can do the tokenization. So this is a transformation from text to ID. ID are just integers, and then encrypt the integers. Once this is done, they can send this to a server where embedding is being run, and the first part of the attention can also be run. Or if you want to actually achieve the attention, you can as well, right? Once this small part is done, you can go back to the client, execute what you want in the clear where there is no weight, so no IP, and then send this back to the server. And the server is executing the part where there are IP, right? This also allows us something quite cool, is that if we push this to the limits, to the extreme, we can actually outsource the whole memory problem that are currently there in LLMs to a server. So what this means is that you won't need as much RAM to run this locally. You can actually export the whole thing on the server and just run the attention stuff, and it will be fast because FHE for linear parts is very fast, right? And so this keeps going. So you have a lot of different layers, and you can keep doing this communication with client server for as many layers as you want. Great. So now it's time for a little demo. So we had an actual demo that we wanted to run, but I tried the Ethernet earlier, and not good enough. And you're gonna see why. So here I'm on my computer. I'm on the server here. And what I'm going to do is just launch the server, right? It's something that listens for any kind of ciphertext coming in, right? And here I'm on my laptop. So what this does here, it's loading the Llama 3 7 billion parameters, but only the parts that are not on the server, right? So I'm asking for a number of tokens I want this to generate, and I'm asking what is FHE, right? So if we go back to the server side, so here you're gonna see that it's gonna generate text with this communication between server and sorry. Great. So what you see here is communication with the server. We can observe the first thing is that ciphertext being sent is only 90 kilobytes, right? Because we have a compression on the inputs in FHE. So this is quite cool. Then we have the key. So it's a public key to load to actually execute the FHE operation, and the circuit that we have to load. The circuit is it's something that allows the server to execute operation on encrypted data, right? And finally is the FHE inference of the input that you can see here, which costs us 0.8 seconds here, right? And we are sending, for every new token, we are sending 4,096 different ciphertext. And the results of the circuit is 40 megabytes. So currently, there is no encryption, compression for the results. So this is where I said, let's not do the demo with the Ethernet, is that downloading 40 megabytes with 1 megabyte second is a bit long. So let's continue. So yeah, here you see the iterations. So we more or less do one token every 3 or 4 seconds. So one token is actually not a word. A word can be composed of several tokens. Homomorphic, for example, is 2 or 3 tokens, right? And what you can see now on the client side is that, so first, the question has to be computed. So for what is FHE, question mark, we have to actually do a computation, right? And then the model starts answering. And it says, yeah, FHE stands for fully homomorphic encryption, and it will give you a definition of how does that work. So the model here on my computer only runs a part of the weights, the other weights being located on the server. While the weights are located on the server, I can still run the LLM without the constraints, and the server can keep part of the weights, making the IP still a thing, right? Because with just the model that I have on my computer, I can't run the full inference anymore. I need to ask for the server to give me this layer that I've been hiding. And this also makes the server a good feature, which was not the main point, but it's basically a way to know how many times user use the model. So you can actually do same kind of business model as the under the API models, because you can actually know how many times they query and how many tokens they generate, right? So that's it for the demo. So of course, here the more tokens. So once it started generating tokens, it now only costs the same thing. It's linear. It's not like you have to recompute this big matrix every time. So this is quite cool because you can continue generation and it doesn't cost more. Great.
Yeah, thank you. And so one thing which is interesting in this demo, so once again, it was recorded demo because internet here is not as fast as it is in France. So one thing which is very important here is that most of the time which was spent to have the new tokens was spent just sending the data. It was not spent making FHE computation. It was mainly during the transport. As Jordan mentioned, we are able to compress the ciphertext. So the input, the encrypted input that we send to the server, for now we are not able to compress the outputs. So the outputs are quite big. It's one of the disadvantages of FHE. Which is the reason why the amount of data that we have to send back from the server is large, and so things are slow. But already that's great to be able to make LLMs in a private way and in a way which preserves the intellectual property of the AI companies. So yeah, if you add to keep one thing from this talk, I would maybe encourage you to have a look to where you are using machine learning models in your company, and maybe ask yourself, are we dealing with private data, either your company data or your users' data, and should we try to make it, to offer the same kind of service, but in a privacy-preserving way? Last year, if you were in the audience, we've shown you that it is possible to do that for machine learning models, so linear models, tree-based models, or even deep learning. And here we've shown you that it is also possible to do it in the hybrid setting for LLMs. So really, you can have a look to where it would be useful in your company and try it. Then, as we've said, we are open source, which means that what we have shown you here today, you can try to reproduce it on your site. So there is this blog post that they have written on the Hugging Face. So you are going to see the technical details there if you want to read them. There are also a few other FHE demos there still on the Hugging Face. So it's live demos where you can see the different kind of use cases, and all of this is running on the Hugging Face servers, and it's very easy to try it. And hopefully you will not have a lot of issues trying this. But if you have some issues or if you need our help, we are here to help. So there is a Discord, discord.afhe.org. So it's not only Zama, it's a few AFHE companies who are there and who give support for their customers who try to do things with AFHE. It's a way for you to get support from the developers, but also to discuss with the other AFHE users and maybe try to build things together.
Maybe just a small word. LLMs, you have seen the speed, right? You can expect, if you are programming with LLMs, for example, currently it's still a bit too slow in the sense that you don't really want to wait when you are programming. But there are a lot of different use cases because, well, LLMs are being used everywhere. For example, when you summarize or extract very important information from legal documents, here you have some time and you want the best answer results. So in this kind of context, it's already possible to use these LLMs and have the privacy preserved.
Okay, so that's it for our presentation. Thanks a lot for your time and your attention, and now we are ready for questions. If you want, there is some mic to ask the questions.
Hello. Thank you very much for the presentation. I think homomorphic encryption is a cool new topic that people should be paying attention to. I don't quite understand, though, which intellectual property are you protecting? I mean, in the demo you showed, you're using an open source model. You control the server, you control the client. So the only way for me to be using this is to convince OpenAI or Google to implement that kind of architecture, right?
Yeah. So a few points here. You're right. I'm using an open source model, and using it as is, it's not very useful to actually protect anything because the weight is public, right? But the first thing is that companies are fine-tuning their model, right, on private data. Once they have fine-tuned their models, they probably don't want to release the information. So some companies have very private data, and they create models that achieve good accuracy in this specific area, and they sell this, right? So that's the first point. The second point is that you're right. There are many companies today that have private models, and this kind of solution is mainly for them. They have models, so if you want that, you have to convince the big companies that have huge models to actually implement that. That's right. But there is a third point, and this third point is there is maybe not something about the IP in this third point, but if you want to run large language models, currently you have to do this locally, right? Or you don't have privacy. This is a bit of a nightmare if you want to execute anything on your smartphone, for example. So what you can do is export all the weights, all the parameters, so you don't have to actually load anything in the RAM memory. And you can execute the whole thing that we presented with a server which will execute all the weights like on the server using FHE so that you have privacy implemented. Right?
Cool. Thank you.
Thank you. That was helpful. His question was quite helpful. My other question is just on the practical aspects of it. There are two questions, actually. So first, I'll ask the practical question. That is, this is going to be incredibly expensive, in my opinion, right? The FHE part you talked about, right? The computation part. So for it to be practical, the responses from this model, even if it's a private model, has to be within maybe a few milliseconds or maybe seconds. But have you done any tests with lots of real-life data where a query goes in, encrypted query goes in, this encrypted thing happens and responses back within some reasonable time? What's the data out there?
So I would say on the price thing. So today you're right that things are a bit slow and so expensive. We are working on making things faster and faster. So so it's not exactly the topic of today, but for example, on Cypher, which is a big machine learning model that we are using as a benchmark at Zama, we have seen improvements from 10 hours to 40 seconds in like 2 years of development. So we are seeing a lot of progress on the speed thing. We hope to see even more progress in the future, maybe not at this scale, but continue to see progress. And in particular, we expect the hardware accelerators, which are made by other companies, like including big ones like Intel and so on. So when those hardware accelerators are there, we will integrate them into our stack, and things will be faster and so certainly less expensive.
Got it. One other question that I have is the hybrid model that you talked about towards the end. At least I'll have to go back and read your blog paper, but it looks to me that part of the zero trust thing is lost there, because I think when the client sends it to the server side, somehow the server is figuring out the entire context, whatever I sent in plain text later, because it has to decrypt it to it. That's at least what I understood. So it appears to me that way. Maybe I'm wrong because of the.
So really, when we send the data to the server, everything is encrypted with AFHE, so the server doesn't see anything. It's just, okay. The only thing which is see is that like the shape of the data, but it's, it's already in the definition of the LLM, there is no secret there. All the data are encrypted, and never in AFHE, the server has the key to be able to decrypt anything. So it's mathematically impossible to decrypt anything for the server.
Got it. Cool.
Okay.
Thank you. This is great. Thank you.
Other questions?
Thank you for the talk. I have a question regarding the what's the name? The weight protection that you provide. You said like it's I think 7% of the IP. 7% of the IP is located in the weight. I think in the attention phases.
Okay, so.
And yeah, my question is going to be like there are two people doing the attention phase in the scheme that you show. Like, is any of it revealed because the client is doing the attention phase, for example?
So in the attention phase, there is like specifically the formula of applying the attention. There is zero weight, nothing, right? The weights are located just before the complicated formula, where they do linear projection, right? Okay. This is one part where the weights are located. But 100% of the weights are located in linear parts. This is what is very fast to execute in FHE. That's why we can actually split them and put them on a server.
Okay, thank you very much.
Hi. When you're talking about IP, you're kind of imagining kind of a malicious client, really, right? Like in some sense. Have you really thought about like circuit privacy as like a cryptographic definition? Like what if the client is not generating authentic ciphertext and is really trying to extract the IP? Have you thought about that?
Yeah. So first, I don't know if you try to extract anything from ChatGPT, but this is quite hard. You extracting the weights would basically make, well, the whole business model behind OpenAI like irrelevant, right?
Sure, but people have done like training set extractions on like
exactly,
these, right?
Yeah, right. And basically nothing prevents retraining on the model output. What you will pay, though, is the cost of inference. So if you want to retrain on ChatGPT outputs, you have to pay for the price of doing millions of inferences. If this is something you are willing to do, then the cost of extracting the knowledge is going to be quite huge. Right?
Okay, thank you. Thanks.
But yeah, I get the question. I get the question.
Okay, so I think there is no more question. Thanks a lot for your attention.
Thank you.